Our first keynote speaker, Nate Foster, is an associate professor of computer science at Cornell University. He is also the chair of technical steering team for P4 project. His contributions to the P4 community have been widely celebrated and shared throughout the years. Nate, thank you for joining us.
Thanks, Sedef, and welcome everyone to this first talk of the P4 Expert Roundtable series. Okay, so I titled my talk P4 at the Edge, and perhaps I could have called it P4 on the Edge as well. So what do I mean by this? Here's a picture of someone skiing down a mountain at the edge. And if you go to the dictionary, it will define the edge in many ways. One is in the sense that we often use edge in networking to mean, at the perimeter, the place or a part that's furthest away from the center of something. And that's one sense of my talk. One trend that we're seeing with P4 is that there's a lot of interest and innovation happening, of course, still in the center of the network, but especially now towards the edge. Things like NICs, up in the kernel, even in user space. Packet processing and network abstractions are becoming really important. And so the edge is where a lot of the action is. The second sense of edge is, of being on edge or on the edge. And here the dictionary says it's that the point or state immediately before something momentous occurs. And so I often feel like P4 is gathering momentum and on the edge of something momentous. And I really feel that now. This language was sort of incubated in the domain of, sort of hardware-oriented routers and switches, but it really feels like it's about to escape out and gain momentum and become really a lingua franca for packet processing more broadly. So I'm quite excited. So I want to use my talk to give you a really broad overview to sort of the state of P4, what's happened in the last year, and a sense of where we're going, as well as this kind of broader perspective on the directions that the community is going to follow. So just to give you a kind of summary of the state of P4 in 2019 and the first part of 2020. At a high level, so the core specifications for the language, the control plane APIs, and things like applications like in-band telemetry. There are working groups made up of a wide swath of community members who work hard on proposing and developing new technical features and then turning those into specification documents that others can read and build on. There's also a growing set of developers who are actively contributing to our open source software packages. And this is, of course, very important because having things like the P4 compiler or different reference implementations of a software switch lets new members of the community or people who want to build products or applications based on P4 get up and running very quickly. We've also seen some new targets this year. I'll highlight these later on, but just to say both of these are focused on the edge. So it was a surprise to me, some folks at Orange contributed a new backend for the P4 compiler that generates code for kernel bypass running a BPF switch. So that was very exciting. And Pensando joined the P4 community this year. I'm sure many of you know Pensando. They have a very full-featured programmable NIC called the DSC. And that's another place where they're looking at P4 programmability as the way to express packet processing on their device. Besides new language features and new targets, we also saw a lot of work on the application side. And here's also where I feel like there's this momentous shift about to happen. So the current focus of the application working group that is chartered under the P4 TST has largely been focused on telemetry. So trying to standardize how collection and processing of telemetry data should work in the P4 setting and more broadly. And what we're starting to see is that people are building applications based on that kind of telemetry data. So the ability to gain real-time precise visibility into exactly what's happening in the network is this kind of superpower that lets you rethink lots of the critical pieces of the networking stack. So one kind of obvious idea that many people are pursuing is, how do we rethink about congestion control when the signal that we use is not some limited and indirect way of detecting congestion, but it's actually based on ground truth, where we've observed, connection in the core, and we then use that to inform how we respond at the edge. A similar idea that has been developed by a P4 collaborator at Cable Labs is a DDoS mitigation solution that uses P4 enabled switches and the visibility and control you have there to help defend against DDoS. So this is just a taste of the kinds of applications we're seeing. And I think we're at the verge again of something exciting, where now that these core pieces, the language, software around it, and targets are in place, we can really focus our attention higher up the stack and start thinking of all the amazing new things we can do with programmability. So just to give a sense of where the language is going, language and ecosystem, there's, I think, a quite large shift that is starting to be set in place that's really spurred by the richer forms of state and the richer forms of processing you can do at the edge. So as I said, P4 kind of grew up as this language, starting with things like routers and switches. Of course, there are also support for things like FPGAs and software switches, but the core model was sort of restricted in a way to ensure simplicity and good performance and predictability. And at the edge, there's richer things we want to do that start to look more like general purpose processing. And so a question is how we can sort of have the best of both worlds, retain all the good features of P4 as it is, but also interface with or accommodate these richer forms of processing that arise naturally at the edge. So the language design working group, I imagine, will spend a lot of its time in the coming year grappling with these questions. The folks who are thinking about P4 architectures, there's a renewed effort to think about what standard models for devices like programmable NICs might look like. So there's a group of people who started meeting a few months ago and plan to continue pushing in that direction to define such a standard. The API working group has made a lot of progress. I'll discuss their specific outcomes of this year in a little bit. But broadly, they'll continue to push the idea of P4 programmability and pipeline independence further up the stack. So for example, right now, the P4 runtime API really sits at the lowest layer of a device stack. And above that, you have, of course, a switch OS and other control abstractions and control applications. And so if you're allowing the lowest levels to be specified in the P4 program, that has implications for all the other abstractions that sit on top of it. So thinking about that as a topic for the API working group to focus on. And then lastly, I think a lot of the action will move out of these kind of core underlying technologies for how we do programmable forwarding. And I think we're on the cusp of a kind of Cambrian explosion of creative new ideas at the application layer. So concretely, I think the application working group is going to broaden their scope a little bit. They've been focused on telemetry just to have some technical focus and to be able to pull in the same direction. But it makes sense now that these pieces are in place and there's interest to consider other applications that might be developed by this community, and also just serving as a kind of repository for all of the different solutions that people are building with P4. So what are some of the challenges? I kind of hinted at this in talking about the language design efforts. In moving to the edge, there's just more you want to do, right? You want to do things like track connections or keep state, maybe per flow state. You may want to do transformations of the kind that arise in a congestion control scheme, or you may want to do cryptography. You may want to even keep application logic. And so in general, all of this state becomes richer than the kind of state that we see in maybe the core of a network where, okay, there's some state, but it's still, most of the internet and most networks work with kind of mostly stateless forwarding. So there's this real distinction between kind of traditional packet processing in a mostly stateless manner and the richer forms of state that arise at the edge. And so, we want P4 to evolve to accommodate both of these kinds of programs, but there are hard technical challenges. How do you represent that state in the language? What kinds of constructs do you need for dealing with it? Do you have distributed state, replicated state? Do you have to worry about consistency? All of these tricky issues that arise in general purpose settings now become challenges for P4 as well. A related challenge is expressiveness. So, P4 intentionally, and you can even argue as sort of its core principle, is based on a really restricted model. There are no pointers, there are no loops, and you can still say quite a bit. So it has, expressions and statements. You can define externs that give you arbitrarily complicated behaviors. But the core language is really defined around this, these primitives that are limited. And that's important because P4 is relatively easy to map to hardware targets, and that mapping is moreover predictable, so programmers don't get super surprised when the compiler has to do things to make their code fit. But if we're going to move to the edge, then we do need to do things like potentially iterate over some kind of dictionary or some rich stateful object, or do operations that might be too expensive to do on a core router, but make total sense on a NIC sitting at the edge, like running a congestion control algorithm. So how do we add to P4 some features that let us express those computations in an elegant way? And to be clear, P4's existing architecture notion lets us get pretty far. So if there's specific primitives that we want to add, we can always add those in an architecture and then invoke those procedures. But there's also, it makes some sense to think about how we might not require everything to be farmed out to externs. And now we have this kind of clash of two different styles, a very restricted style and a very more general style. So these are challenges for the community to look at. And then the kind of cross-cutting challenges are, how do we do this in a way that lets people write code in a modular style? So how can we, have libraries of P4 code that people can draw on so that they're not writing from scratch applications every time they want to do something new? I think that's really essential for enabling programmers to be productive and to build all these applications that we think they will. How do we make code portable? So I don't come historically from a networking background. I was trained in the languages community. And there's, I think, a real difference between the kind of code that you see in general purpose computing, in Python or C++ or Java, where, these days, you don't really think too much about the underlying machine you're running on. Is it ARM? Is it Intel? Is it something else? In the networking domain, for good reason, we tend to be very aware of the targets that we're running on because performance is king. And so that tends to mean that code is not very portable. But if we're going to really move forward and have things like libraries of P4 code and applications structured in modular ways, then we need to somehow get past that. We need to find ways to let people write code that somehow is target and perhaps even architecture independent, that captures some nugget of packet processing or stateful computation of some way, and to allow that code to be retargeted to different underlying devices. And I think that actually P4's design accommodates this. So being a network-focused DSL that's reasonably high level, it's got a pretty simple model of state, and it's got fairly standard operations on that state. That leaves a lot of space for a compiler to do the mapping to different targets in reasonable ways. So I think there's an opportunity here, but there's some technical challenges to be solved. And then the last kind of ability is predictability. One reason that I think a lot of people like P4, especially as compared to other packet processing frameworks, is it's high level and declarative and all of these good things, but it's not so far away from the underlying device models that when you write a program, you have a pretty good sense of how it's going to run. So how many resources will it need, and what kind of performance can I expect? And if we move to these richer settings, then that same kind of easy predictability will be more challenging. So I don't have the answers to all of these, but I think it's a really fascinating intellectual space to work in, and there's amazing opportunities, obviously, to extend P4 to the edge in this way. So in navigating these challenges and working on these problems, there's some guiding principles that I just wanted to kind of reiterate, because I think these are really core to what P4 is about. So the first actually have nothing to do with technical matters and about the community. P4 started out as a really grassroots kind of organization. Some of you, I'm sure, were at the first P4 workshop at Stanford, I guess more than 6 years ago. And it was a really small event, and there was a lot of excitement around this language, but it was very clear that this was just a group of enthusiastic people who wanted to push programmability into networks from academia, from vendors, from cloud providers. There was all perspectives represented there. And so one of the things I love about the P4 community is it's really open to anyone who wants to participate. If you come to our working group meetings, it's not like typical standards bodies where you have different companies all sort of pushing their perspective. I think it's truly a dialogue around technical matters, and decisions are made by consensus and based on technical merit, which is great. And so I personally value that aspect of our community a lot, and I think that that's an important thing for us to continue having in our community. Another sort of strategic goal is, I think P4 has become a de facto standard for low-level packet processing in certain domains, like say on programmable routers. But if we want to broaden the scope where P4 can be applied, in particular to things at the edge and in software, then there's all these challenges we have to solve. And I think it'll be important for us to find synergies with related efforts. So, as for those of you who are doing work already or thinking about getting involved, it's important to have a very ecumenical and kind of open mind here. So, finding ways to leverage efforts like the ONF, which has a large and mature open source software stack, things like Onos, Trellis, all these designs and running code that you can download and run today, as well as related efforts like eBPF, which has a huge and enthusiastic and very amazing technical community around it, or XDP. The list could go on. DPDK, VPP, all these different frameworks. They all have good ideas, and so finding ways to incorporate these good ideas, even link up with these communities, I think will be critical for our success, because there's a lot of hard problems to solve. And then more at the technical level, the kind of core philosophical principles that P4 has been based on, and I think it would be a mistake to throw these out, is that P4 is a domain-specific and sort of declarative language that has clear semantics. So unlike some other languages that are sort of defined in rather ad hoc ways, fairly low level, and it's kind of unclear what things mean, P4 has always kind of been based on this idea that it should be high enough level that you kind of capture the notion of declarativeness. You say what you want to happen to your packets. You don't really specify the nitty-gritty low-level details of the how. And also that each of these constructs has at least a clear meaning. And there are folks like Stefan, who has talked next, has used P4 at Google as a modeling language, and using the fact that it has a clear semantics to drive development of different kinds of validation tools. So I think that's a really important thing for us to continue, even as we reach out to more technical ideas and other forms of packet processing. Another thing that I think is really important, and I think a real strength of P4, is it's a domain-specific language. So it doesn't really look like assembly or C. It's got things like pipelines and parsers and header types. Of course, it also has the things that are found in standard languages, because at the end of the day, we're writing programs. But I think these domain-specific constructs are really powerful, and they let practitioners kind of think in fairly high-level and intuitive concepts for the domain. So the challenge here is, as we move to the edge, what are the new domain-specific constructs that make sense for that domain? For basic, mostly stateless packet processing, I think P4 mostly has it right. Parsers, match action tables, pipelines, and so on. But if we extend beyond that, what are the expressive enough but still limited constructs that will be natural for practitioners and compilers to work in terms of? And then lastly, I've already touched on this, but P4 really gives you a nice notion of predictability, both in terms of how many resources are going to be needed to implement this on certain kinds of targets, and what kind of performance are you going to get. And as I said, performance is king in networking. If you have a language that's beautiful and has a clear semantics and domain specific, but it's slow, no one's going to use it. And so this last challenge, I think, is really critical as we move to these richer forms of processing. How do we not, throw out all the nice performance-oriented aspects of the existing language? Okay, so that's sort of my summary of where we are and where we're going and how I think we'll get there. So I want to shift gears now and do something that we do every year, which is to recognize folks in the community who have really gone above and beyond this year and even beyond in contributing to the community. So we have this tradition of giving a distinguished service award. Usually we have a nice piece of metal or a nice plaque to give them. I don't have virtual plaques besides this emoji, so you'll have to bear with me on that. We'll ship some real plaques to the winners. So I'm pleased to announce that this year, the Distinguished Service Award goes to Mihai Budio at VMware Research. And I have some virtual applause here to play for Mihai. So as I'm sure many of you know, Mihai's been a member of the P4 community for many years. He's actually one of the people who was a key designer of the P4 16 language. So as P4 grew up from P4 14 to P4 16 and really became a mature language with expressions and statements and types and architectures, a lot of that is due to Mihai's design. Mihai's also I think it's fair to say, primary developer of the reference compiler. Certainly if you look at contributions on GitHub, and certainly if you look at the speed between which people report bugs and they get fixed, usually by Mihai, he's the person who's there doing things from solving really minor bugs to doing major refactorings. And that's really important because the compiler is one of the main pieces of software that we all rely on. And so Mihai's efforts go a long way. And he's also co-chair with me of the Language Design Working Group and does a wonderful job of moving designs and the spec forward. So congratulations, Mihai. We'll send you a plaque, and we're really grateful for all of your contributions. This year, I'm pleased to also offer a second service award. So the TST couldn't decide between these two excellent contributors to P4. So the second one goes to Antonin Voss. Play my applause again for Antonin. Sorry, my phone is slow. Yeah. You will get... Okay, so Antonin also has been around for a really long time. I'm sure many of you know him through his work on P4. You can almost parallel Antonin and Mihai's contributions. They're on different parts of the ecosystem, but very similar in style. So Antonin is, again, one of the key designers of P4 Runtime, which is the control API that the community's developed over the last few years. I know he's the person who's been driving meetings, writing the spec, pushing out new versions. He's also the main developer of the BMV2 software switch, which many of us use as we're developing P4 solutions. And he also chairs the P4 API working group. And like Mihai, he's one of these people who has really shaped the direction of the community. So thank you, Antonin, for your great contributions. And we'll send a couple of plaques to VMware for both of you to enjoy. So thank you again. Okay, I have just a few minutes left, so I want to quickly go through slightly more technically some of the updates that have happened at the working group level in the community, and then I'll turn it over to Stefan for his talk. So the Language Design Working Group published a new version of the language spec last October, and a lot of the changes here were kind of ergonomic improvements to the type systems to support some use cases that came from application developers. Also a lot of work around annotations, which are used by compilers as pragmas, used to provide hints to things like the runtime. So there's a lot of work here. And there's another revision of the spec that should be released very soon that will again make some improvements to how types and expressions and computations work, especially around the data types. So structures, which are used to organized lots of headers and metadata. These are kind of the core, the workhorse that lots of programs use to get their job done. And we've developed a number of features to make these easier to work with. On the software side, there's the P4C UBPF backend that I'll mention a little later. And there's also been some really nice work by a grad student, Fabian Ruffy, at NYU. And Fabian has been doing differential testing of the front end of the compiler and found slews of bugs. So this is really greatly appreciated and has really improved the quality of the P4C front end. I'll briefly go through the future plan. So there's some proposals already to extend P4 with a simple form of a module system. And there's some work on adding specifications of the behaviors of architectures that's ongoing. So we imagine that these things will go into a future revision of the language probably later this year. For the API working group, they also just released a new spec, version 1.1.0. And the big change here was overhauling the master arbitration between the controller side of things and the switches. There's also some new RPCs for querying capabilities, better support for multicast, and so on. They actually are almost ready to release another minor version, so version 1.2.0. And here they've added support for optional match kinds, some additional annotation tweaks, and new language bindings. On the software side, the major achievement here is that Stratum, which is a control based on P4 runtime, was released as open source last fall by the ONF. And so if you want to work with P4 runtime using an industrial strength control system today, Stratum is the thing you can use. In the future, the API working group is actually considering the next major version, 2.0. So if you're interested in, if you have ideas for features that should be part of 2.0, join their meetings. I believe they're on Wednesdays. And the floor is open right now for major new features. The architecture working group, as I mentioned, has some renewed interest around what a portable NIC architecture might look like. And so there's some discussions that have started and some kind of initial designs that are being proposed. This is a design that Andy Fingerhut produced as part of these discussions. So the idea is to take something like the portable switch architecture, which was published a couple years ago, and try to generalize it a little bit. So you could imagine mapping it down to a programmable NIC. So right now there's, again, it's fairly early design work. There's a lot of effort around identifying use cases, trying to standardize some of the common functions and blocks for a portable NIC architecture, and then eventually thinking about what kinds of language extensions we might need. On the software side, there's some continued work building an open source implementation of PSA on P4C and BMV2, and we expect that to converge fairly soon. On the application side, there's been another major revision of the in-band telemetry spec. And I just want to sort of pause and say, when this group was chartered, the idea of telemetry was kind of in the air, and there were multiple solutions out there. I think this group, really crisply articulated what INT is, kind of at the conceptual level, and also did a lot of the hard work to define a spec that is now being adopted. So it's a real success case for the community. The new version that they're going to release any day now has new forms of transport, metadata, and operation modes. They've aligned with some IETF standards and have additional support for coalescing the INT reports into a single packet and some extensions that give additional flexibility to implementers. So this is a great success. I know there's been a ton of work by J.K. Mukesh and the other members of the working group. Folks from Cisco and Cable Labs have been contributing, and it's really exciting to see this reaching fruition. Looking ahead, the group plans to focus on some end-host centric use cases of INT, and also things like closed loop transport and congestion. Okay, so I have just a couple minutes, so I want to quickly cover some community highlights. I've mentioned these before, but I was very excited in the last 6 months that a couple of sort of unknown to me surprise new members of P4 emerged. One was Pensando, and we'll hear some talks later on in this roundtable series from Vipin and Mario talking about Pensando's device and some of the use cases. They also have a blog post that's linked here on the bottom of my slide. So they built a new kind of programmable NIC that combines a P4 programmable pipeline for doing basic packet processing with a bunch of general purpose cores that can be used to do much more. So I think this is super exciting. As we heard last year at the P4 workshop from John Hennessy, the only way to deal with the growing gap between, say, network speeds and CPU performance, which is sort of tapering off due to Moore's law, is to have domain-specific accelerators. And in the case of network programming in P4, closer to the edge, there's a lot of opportunity to do richer forms of processing. You're not dealing with as many flows as you are at the core. You have a bit more of a budget to do some more processing on every packet. And so Pensando's device is an attempt to produce something that can do that richer processing. And I think it's really exciting. There are lots of questions here. How should P4 evolve to accommodate these general purpose constructs? How do we manage all the state on this device? How do we reason about performance? And these are things that the language and architecture working groups will bang their heads on for the next few years. But I'm really excited to see this, and tune in later for Vipin and Mario's talk to hear about use cases and also the details of their target. Another exciting thing that emerged, again, as a surprise to me, was Orange produced a new P4 to UBPF compiler. There have been several previous BPF compilers from Mihai and others at VMware, but this one is now integrated into the master branch of P4C. It's very full-featured. It's based on a fairly standard architecture model, just 3 stages: parser, match action, deparser. And it enables using P4 with various forms of kernel bypass, so DPDK, XDP, and so on. And so I think it's a really exciting opportunity because it lets us get the flexibility of BPF style processing with the performance of P4. Another kind of exciting thing is often people are interested in extending P4 with some new features. And I think this is a software framework that might make that easy. The folks at Orange have already experimented with implementing new externs that get called out to from P4. And this is a nice framework for doing that in a really lightweight way. So if you're interested, check it out. It's already on GitHub as part of the P4C repository. And then lastly, I thought I'd highlight one paper from the academic community. This is a paper that was presented at the buffer sizing workshop at Stanford last year. And it uses P4-enabled switches to give end hosts precise feedback about congestion. This is, of course, an old idea. There's things like ECN that have done it for years. But what's new here is that we can do it in a more rich way and with more precision than has been possible in the past. And it's all done just by writing a P4 program. There are a bunch of challenges. How do you collect this rich data in a scalable way? How do you avoid losing the signal from the noise when you have elements and mites flows? How do you fairly share resources like queues? And how do you avoid making this new system so complicated it becomes a source of faults like incast or security vulnerabilities and so on? But the opportunity is, now that we can gain this precise visibility in the network using things like telemetry and this form of congestion feedback, how should the control loop evolve? How do we think about end-host congestion control schemes, and what becomes possible that wasn't before? Okay, so I'll wrap up because I'm short on time. I just wanted to thank everyone who put this together. We've had this workshop for many years, and obviously with coronavirus this year, it wasn't clear what would happen. But Guru, who was the general chair of this workshop, had the vision that we could still have an event and have a forum for exchanging ideas in the P4 community. And I think it's working quite well. Larry Peterson from ONF and Anirudh Sivaraman from NYU did a great job of soliciting contributions from the whole community and reviewing those submissions and picking about, I think, a dozen that we presented. This really, again, showcases the breadth of ideas that were developing the community, but it took a lot of hard work on their part to curate that program. And then there's a whole cast of people who did all of the non-glamorous work to put this together. Moving to virtual, you might think it's less work than doing an in-person event at Stanford, but there's just so many moving pieces and failure modes that it takes a lot of planning. So Sadef, who has been involved with P4 for a long time, has done a wonderful job of putting this together, coordinating the speakers, doing dry runs, as well as Denise, Rachel, Michelle, and Timon from ONF and Intel have helped out with the organization. And I also want to thank our sponsors, Google, Intel, and Stortis, that provided the funding that makes this event possible. Okay, so just as a closing kind of call to arms, I think many of you are part of the P4 community already, but if you're not, you should join. There's no fee to participate. The only thing you have to do is to sign a lightweight legal agreement that's basically the Apache 2 license, just says that your contributions are given to the community under that license. Of course, it's possible to explore upgraded versions of ONF status, such as being a collaborator or a member. And we have some collaborators focused on the P4 project right now. So that's a way to sort of deepen your involvement. Join the working groups. That's where all the action is right now. Anyone with a good idea can help shape the future of the language. We have an open governance model, a code of conduct. It's a great community. And contribute to P4 software. Of course, there's lots of things that happen, in proprietary settings at companies. But one of the really cool things about our community is that a lot of our ideas get out there in these open source platforms that are then picked up and used by others. Okay, so I'll thank you for your time and stop there and take maybe, we'll take maybe 5 to 10 minutes to answer questions.
Hi, Nate. So we have a few questions from the audience. So how much of state does P4 language support today? That's the first question. There are applications surrounding IP fragmentation reassembly, traffic shaping, and sequence delivery. Security packets require preserved state. Is this possible in the near future? Is the first question.
Yeah, so P4, since the P4.16 revision of the language, has actually been a family of languages. So if you're new to P4, you may not realize this. If you're an old hat, this will be review. But just to explain the history and kind of what things look like technically, P4.14 was really based on the PISA model. PISA stands for Protocol Independent Switch Architecture. And the idea was that there's a parser at the beginning that's programmable, and then a series of match action tables in the middle, and then a deparser at the end. There's, of course, a widget in the middle that lets you do forwarding and cloning and so on. But P4.14 was really tied to this architecture, and it exposed as primitives a few of the things that are commonly found on routers, like counters and meters and registers. But otherwise, things were kind of baked in. So in P4.16, the community realized that, first of all, even if you just restrict your attention to routers, there are, and switching chips, there are many possible designs. And so having a one-size-fits-all abstract architecture might not be the most efficient way to go. And so the language decoupled the programs that you write from the architectures that they run on. And then below that, a single architecture might be implemented by several different targets. So that separation was important. And it also opens up the possibility of having different features that are supported on different kinds of architectures. Today, the architectures that are most widely used are either proprietary architectures provided by specific vendors, or things like V1 model or PSA, which are some of the open source architectures. And these only expose state through registers. So basically finite arrays of data that are indexed into positionally. And so that's, I think, the main limitation for sort of, if you take P4 to be one of these architectures and that notion of state, there's only so much you can do with statically allocated fixed registers. Even things like tracking connections, tracking the set of active flows. Doing that exactly would require something like a dictionary structure or a hash table, which you can't really implement fully faithfully with just a fixed array. And so that sounds like a limitation, but there's fairly simple things you could do. So if you have a target that supports something like a hash table, you can expose that today with no language changes in P4 as a new kind of extern. And you have to decide what operations that data structure supports and maybe how efficient those are, but the language itself can accommodate it. So I think this question's spot on. I mean, there are kind of coming down from applications, there are all these use cases that require more than what at least the V1 model and PSA and these kind of traditional open source architectures provide in terms of state. And we'd like to identify and flesh out, what are some of these use cases, and then find, I think, the simplest and most efficient ways of exposing some primitives that would let us implement them without going all the, we don't want to go to C. We don't want to have a heap with pointers and dynamic allocation because that would mean that programs become unpredictable to compile, unpredictable to run, hard to reason about. So I think that finding the right state that gets us beyond this kind of statically allocated registers is what will nudge us forward to the edge.
Perfect, thank you. I think we have time for one more question. Are NICs that use P4 mainly just programmable ASICs, similar to, let's say, Barefoot Tofino chips in case of switches? Or are there other NIC architectures for which it also makes sense to use P4?
Right. So I should say up front that I'm not a hardware person or a NIC person, and I really have limited knowledge of what's going on in industry with programmable NICs and their architecture right now. The simple understanding I have is that there are NICs that have a pipeline that at the hardware level looks similar to what, say, Barefoot's Tofino chip looks like. And so you can imagine a P4 programmable pipeline that's sitting next to or coupled with some more powerful either fixed function units or maybe even some cores. They might have some other memory interface that can be used. So that's one possible model. As far as how P4 might be useful for multi-system on chip kinds of things, my sort of uninformed answer is it seems like what P4 is good at is expressing declarative processing of packets or messages in these restricted ways. So I can imagine ways of using P4 in those settings, but I would need to do more studying to understand how that would work. Let me go through, there's a bunch of questions now, and we can do some more at the end. Let's see. So there's several high-level questions, I think, from newbies. So maybe I'll take this last, and it's sort of about how P4 relates to SDN and OpenFlow. And I actually would encourage people, there's some very nice blog posts from a couple of years ago on the P4 website explaining sort of why P4 and how it's different than OpenFlow, and what the relationship to all these different ideas are. The very high level thing I would say is, I got involved with SDN about 10 years ago, and to me it was very natural to think about opening up these network devices that have been sort of closed and tightly vertically integrated for so long, and to think about how we could sort of separate concerns and restructure the data plane, restructure the control plane in a different way. So OpenFlow was an attempt to do that, and at least in terms of kind of conceptual contributions and mindshare, it obviously had a huge influence on the industry. But the early versions of OpenFlow, of course, were kind of too simplistic to handle all the features that people need in their data planes. So the original OpenFlow was, a single match action table that handled about, I think, a dozen fields and had sort of some canned procedures you could run as the actions. And people very quickly figured out that that was too limited. And then you had type tables and pipelines, and it started to look P4-ish, but it was kind of evolving in a way that was just accreting features. So the P4 language, I think, is a clean slate attempt to figure out, if we weren't taking the baggage of existing data plane SDKs or router SDKs or things like OpenFlow, and we just thought, what would be a good programming language for writing these data planes? What would it have? That's what P4 is. So I do view it as an evolution, but maybe a revolution, a replacement of things like OpenFlow. But of course, they're sort of based on similar underlying principles, and there are ways you can sort of convert between them. So some of the later OpenFlow standards have features that resemble P4 features, and it's possible to encode at least some versions of OpenFlow, or at least some of the features in OpenFlow as P4 programs. So I think they're closely related, but I would say P4 is a kind of clean slate design. Okay, in terms of time, I think I should stop there so that we have time for further questions at the end. So thank you for joining. And again, let me congratulate Mihai and Antonin for their service awards. We really appreciate their contributions to the community.